Hey everyone. Tonight I just wanted to start out by outlining the process by which you do force problems, and then we're going to apply this process as we work on a new type of problem. Okay? So here we go. First part of this video, steps to solving a force problem. Okay, so step number one, you need to draw a free body diagram. You need to look at your situation, figure out what all of those forces are, and label all of those forces. So step one, free body diagram. Step two, from your free body diagram, you need to separate the forces in the x and the y direction, okay? And then you need to sum up all of the forces in the x and the y direction. So we're going to sum up the forces in the y direction. We need to figure out what that equals to. And we need to sum up the forces in the x direction and figure out what that equals to. The third step is we're going to figure out what that variable is, and we're going to rearrange our equations, plug them into each other. Basically, at the end of the day, we need to do some algebra. Is that how you spell that? So you have to do some algebra, rearranging your equations and figuring out what you're solving for. And then at the very end of the day, finally, you can plug in your numbers and solve. Okay? We're plugging the numbers at the very, very end. Okay, we're plugging numbers at the very, very end. I'd like to see you do that. Okay, so we're going to always resort to these 4 steps when we're doing a force problem. Okay? So here we go. Part 2. So this problem is going to be very, very similar to the problem we did last time when we were looking at the acceleration of Ben as he rolled down the hill. Only this time we're going to look at something that's resting on an incline and the forces that are acting on it. We need to look at all of the forces that are acting on this object that's making it so it's not moving, so it's in a static state. Okay? So let's draw the free body diagram of this. Okay, again, make your free body diagrams nice and big, because more oftentimes than not, you're going to have to do a little trigonometry on them. So we're going to represent our object with a single dot. This is step 1. We're going to draw our free body diagram. Here we go. We know that this object has some sort of mass that's pointing straight down. So we're going to draw that force. And a lot of you want to label this force straight down the force of gravity. Okay? But gravity, remember, isn't a force. Gravity is an acceleration. Okay? In order for it to be a force, we need to multiply it by the mass. So this, we can call it W, or we can just plug in mg right away. This is the weight force. Okay? Next, we know we have a normal force that's perpendicular to the surface of our inclined plane here. So we are going to draw a normal force that is perpendicular to that plane. Okay? We're going to call it capital N. Now we have to ask ourselves, if this was a frictionless surface, what would the box be doing? Well, naturally the box would be sliding down the incline. And we learned last time that was because it was the component of the weight force pulling it down the incline. Okay? But now it's sitting still. So what is the force that's opposing the motion? What is holding it up? Well, I've already kind of said it, but the force that's holding it up is friction. So we need to remember one thing important about friction. And that's friction always goes the opposite direction of the motion. So if our box wants to slide this way, it means that friction must be going up the incline. And of course, I'm going to label this with a fancy F for friction. Okay? And because the box is not moving, we're going to call it friction static. Okay? It's the static friction force that we want to use. We drew our free body diagram. Now, we need to sum up the forces in both the x and the y direction. So let's go ahead and do that quick. I've just redrawn the free body diagram here. If our axis was in the normal way, just up and down and left and right, we would have two vectors that we need to decompose using trigonometry. If, however, we take our axis and we orient it just a little bit differently, now we only have one. So I'm going to go ahead and draw in this new coordinate plane. It was like this, and now we're orienting it like this. So now we have two of our force vectors on the coordinate plane here. Like that. This is going to be plus y. This is going to be plus x. So now we drew our free body diagram. Now we need to sum up the forces in the x and the y direction. So let's go ahead and start with just the first one here, summing up the forces in the y direction. So we're going to do sigma. By the way, this is the Greek letter sigma, not epsilon. I've been telling you it's epsilon. I'm so sorry. Sum up the forces in the y direction. And we have to ask ourselves, okay, what is this going to equal? Well, we know that the block on the incline, or whatever it is, we know that this block isn't moving up or down at all. So we know that the summation of all of the forces in the y direction have to be equal to a big old 0, because it's not moving up or down in the y-axis. Okay? Looks like a child drew that 0. So now we list off all of the forces that we have in the y direction. Okay? Well, we have the normal force going in the positive y, so we can leave that as a positive n. We have to come over here and we have to break up this weight vector into its x and y components. So remember that if that's theta right there, that means that this angle is also theta. So we can break up the components here and here. Now a lot of you are drawing it a little bit differently, so just make sure that this angle right here is the 90-degree angle. Okay? So that makes this one over here mg, and because it's the adjacent side, remember we're doing SOHCAHTOA here. SOHCAHTOA, so cosine is adjacent over, cosine of theta is adjacent over hypotenuse. The hypotenuse here is mg. So if we work that out, we get mg cosine theta. That's this side right here. And that makes this side down here mg sine theta. Okay? So now, what other forces do we have in the y direction? Well, we have an mg cosine theta, except now it's pointed down. So it's going to be negative. Negative mg cosine theta. And what is the summation of all of these forces equal? Well, it equals 0. Now let's clean up this equation just a little bit to get rid of this 0. Okay, any other forces in the y direction? It doesn't look like it. So now we can move on to summing up the forces in the x direction. We're going to do sigma, forces, x direction. And we have to ask ourselves, well, what does this equal? Well, we said that the box was not moving. It was just sitting there. So even in the x direction, it's going to be the summation of all the forces has to equal 0. So again, let's sum up. Let's do a little divider here. So we're going to sum up the forces in the x direction. So in the x direction, first off, in the positive x direction, we have this force of friction. In the negative x direction, down the incline, we have this mg sine theta. So it's minus mg sine theta. And we're going to set this equal to 0. The summation of all the forces in the x direction has to equal 0 because it's not sliding up or down the incline. Now let's clean up this equation as well. So we get force of friction is equal to mg sine theta. Okay, now we have these two equations. What are some other equations that we know, some side equations? Well, we know that the force of friction, we know that we have some sort of friction equation that goes like mu s times the normal force, okay? So we're going to have to keep this equation in mind as we move forward as well, okay? So we did our free body diagram, we summed up the forces in the x and y direction. Now we need to rearrange a little bit, and we need to do some algebra and figure out what it is we're solving for. So let's say the question is, I want to know, let's say we want to solve for the coefficient of static friction. Okay, we need to solve for the coefficient of static friction between the object and the inclined plane. So let's use this equation, and this equation to try and find an equation that solves for the coefficient of static friction. So now we're going to be doing some algebra. So if we look at this equation here, we will see that the force of friction is equal to mu static n. So we're going to take this equation and we are just going to dump this right into there. So let's rewrite this equation over here using the friction equation with it. Okay, we're solving for this. We could probably figure out the mass of the box. We know what gravity is. We know sine theta. We don't know what the normal force is, though. But where do we have an equation that gives us what the normal force is equal to in terms of quantities that we know? Well, right here. So let's take this equation, the normal force here, the normal force here. So let's take this and plug it in for that. So let's rewrite it again. Remember, we're just doing algebra right now. This isn't any physics. We already did the physics. Now it's just a matter of algebra. So we're going to get okay, and remember we're trying to solve for mu s. So let's go ahead and solve for this. So mu s is equal to, we're going to take this, we're going to divide both sides by mg cosine theta, because we're trying to get this by itself. So mg cosine theta. Okay, so obviously this all cancels with that, because we're canceling it out on purpose. And if we come over here, look at this, our m's cancel, our g's cancel, and we're left with sine theta divided by cosine theta, which if you remember your trig identities, we can get that the coefficient of static friction is the tangent of theta. So the coefficient of friction depends on whatever angle that the ramp is at. So now we found our expression, our equation for whatever it is we were trying to solve for. So now we can plug in our numbers and solve. Let's say theta was 15 degrees. You get mu s is tangent of 15 degrees. So